Hi, I'm Ken Shackle, and you're not. But enough about you and me. We're here to talk about one thing, plants. Plants and water, two things. And evaporation, three things. So here's a plant. It's a very nice plant. It's green, it's photosynthesizing, it's growing. Now, if it's growing, you might think it should be gaining weight. And as far as the plant is concerned, you'd be right. But if you put the plant on a scale and weigh it, what you find is that it's losing weight. Plants do this all day long. Some even do it a little at night. Okay, why is the plant losing weight? The plant's losing weight because water is evaporating into the air out from inside the leaves. This is called transpiration because it's evaporation of water that's sort of transiting through the plant. Now, why plants transpire is a whole nother subject that I can't talk about right now. But I will say it's not just to keep themselves cool, and this particular fact has driven plant evolution, ecosystem functioning, the presence of animals on the earth, agriculture, civilization, basically the meaning of life. But for now, we're just going to talk about evaporation. And to do that, we need to set up an experiment, so let's go inside. So, why does water evaporate? You may be thinking, well, the water is wet and the air is dry, which is true. But you can take a glass of hot water and a glass of cold water and put them in the same air, and the hot water will be evaporating water into the air, but the cold water, if it's cold enough, will actually be condensing water from the air. So it's not a question of the air being dry. It's a question of whether the water in the air is in equilibrium or not with the water in the water. What does that mean? Okay, so here's a jar that has air and water in it. It's been covered for a long time, and as far as we can see, there's no change happening in the air and no change happening in the water. But that doesn't mean there isn't anything going on in there. Air is a gas, and gas molecules are always bouncing around, kind of like ping pong balls, in the space available to them. So what molecules are in there? Nitrogen, oxygen, CO2, blah, 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 right? Well, some of those molecules in there are water vapor molecules. And that's what I mean when I say the water in the air. It's referring to those molecules. Now, this is where the story gets interesting, I hope. Because you might think that once a water molecule got into the gas phase and started bouncing around with all the other ping pong balls in there, it might stay there. But in fact, it's constantly exchanging places between the gas phase and the liquid phase. When just as many water molecules leave the gas phase and go into the liquid phase as there are molecules that go from the liquid phase into the gas phase, this is what we mean when we say that water in the air is in equilibrium with water in the water. It's a molecular equilibrium. So this is a hint to the answer to our question about why water evaporates. When we say water evaporation, we don't just mean that water is moving from the liquid phase into the gas phase, because that happens all the time. The question is why there is a net movement of water from the liquid phase into the gas phase. And the answer is that they are not in equilibrium. So then we have to decide how we are going to describe the water in the gas phase in a way to compare it to whether it's in equilibrium or not with the water in the liquid phase. Now, gas phase is fairly easy to describe because we have the perfect gas law, PV equals nRT. And for this problem, we describe it as a pressure. But we have to describe it as just the pressure in that gas phase that's due to the water vapor and not all the other molecules that are in there. Right now there's air in there, so there's a lot of other molecules in there. We can measure pressure pretty easily with a pressure gauge, but measuring the partial pressure of water is not so easy unless you do something pretty simple. Boil the water. Okay, so here's our jar of water, It's on a heating plate and it's boiling. We have a pressure gauge on it, and we've also got a temperature gauge. Temperature gauge is reading around 100 degrees C, because that's where water boils, of course. And the top is on kind of loosely, and even though you can't see it very well, there's steam coming out of it. It's a good thing it was loose, because probably by now it would have exploded with the pressure inside. And what we assume is that all that water that's coming out of the liquid phase and going into the gas phase has flushed out all of the air that was inside that jar to begin with. So now what we have is pure water vapor filling the airspace, or the gas phase, let's say, above that liquid water. So there's a very important assumption here, and that is that the water in the gas phase is going to behave the same as it does when it's a pure gas of water vapor as it does when it's mixed with other gases. That is, that gases don't interact with one another. So when we measure the pressure using this pressure gauge inside that pure water vapor phase, we will also be measuring the equivalent of what the partial pressure of water would be at whatever temperature it's at. Now right now the system is at 100 degrees C because the water's boiling, and the pressure inside there is about 1 atmosphere because the lid is open and gas is escaping. Maybe it's a little above 1 atmosphere if there's some resistance to losing the gas. But anyway, the temperature gauge that you see reads actually in negative values from 0, which is where it is now, which is atmospheric, down to minus 100 kilopascals, which is about minus 1 atmosphere. So we should have plenty of range in order to see what we want to see. So I'm going to turn off the water right now. Hang on. Okay, so the water has just stopped boiling, and I turned the heat off, and you can see that the pressure, and I sealed the lid, so you can see that the pressure is starting to go down, and now there's some interesting things happening in the water. The temperature is 90-something degrees C. Now what's going on is that the pressure is starting to drop, and because the system is cooling. And I want to slow down that process, so I'm going to move this to a place where it'll slow down. Okay, so what I've done is I put it into a styrofoam box and covered it with a towel. And periodically we're going to check on what the pressure and what the temperature are. So it started about 2 o'clock, so it's now 2:02. The pressure is, I don't know, about minus 18 something. We'll check it more accurately later. And 98.8. So I'm going to cover this over and let it cool off slowly, and we'll check it a little later. Okay, it's a few minutes later. I just checked the video on the last one, and it was reading minus 16 kilopascals in pressure and 98.8 degrees C in temperature. And I'll do the same thing for this. I won't open it for long. I'll just get a good shot of the pressure gauge. Come on, get in focus. There you go, whatever that is. And the temperature is 95.9. Back in a minute. Okay, it's about 2:40. And let's see what we got. Okay, pressure has dropped to about minus 60, a little bit, maybe minus 61. And the temperature is 79.6. Okay, so I don't know if you've noticed this, but we're better than half of the way from atmospheric pressure to a full vacuum, and we've only gone down, the temperature of the water has only gone down about 20 degrees. So as Artie Johnson in Rowan and Martin's Laugh-In would say, very interesting. Okay, we're cooling off, 69.2 and minus 77. Okay, it's about 3:30. We're down to 59.5 and minus 80, about minus 86.5. So the jar's reached about room temperature now, and you can see that the pressure gauge is actually reading off-scale negative. It's reading a bit more vacuum than there should be, even if the pressure in there was 0, which is impossible, so the gauge must be off a bit. Either that or we've discovered cold fusion or something, I don't know. In any case, it's a very low pressure. This tells us that liquid water at room temperature is at equilibrium with a very low partial pressure of water vapor. If we'd started with air and water in there and just closed the jar, even though the relative humidity of the air would have come up to 100%, the actual water vapor molecules in that air would still be at a very low partial pressure. They would only account for a small fraction of that 1 atmosphere total pressure, and the same small fraction of the actual moles of gas in that volume. Now, this is equilibrium. Water will evaporate if the partial pressure of water in the air is lower than this value, and it will condense if the partial pressure of water in the air is higher than this value. Now, evaporation and condensation are not only important for biological organisms, particularly plants, but also in climate, ecology, engineering, about a million other things. So the relation of water vapor pressure to water temperature has been studied a lot, and there are many ways to graph or tabulate this relationship. This one is called Tietjens' equation. Our data points were below this line, probably because the gauge was off. I'm sure I was reading it right. But anyway, both showed the exact same pattern of increase in partial pressure with increasing temperature. Tietjens' equation is a great way to understand evaporation and condensation. It's also a great way to understand another really important property of water and other liquids, boiling. For any water temperature, when the partial pressure of water vapor in the air matches the line, then you have equilibrium, neither evaporation nor condensation. When the partial pressure in the air is above the line, then water will condense. When it's below the line, water will evaporate. It's no coincidence that Tietjens' line shows a little above 100 kilopascal of vapor pressure at 100 degrees C. 100 kilopascal is about atmospheric pressure. For instance, today, atmospheric pressure at my location is currently 101.3 kilopascals. So, what this means is that when water gets to 100 C, its equilibrium vapor pressure is just above the pressure pushing back on it by the atmosphere. So, it vaporizes as fast as it can. The technical term for vaporizing as fast as it can is boiling. If we lived on a planet with a high atmospheric pressure, the boiling point of water would be higher than 100. Of course, we don't need to go to another planet just to see this. You can boil water at room temperature by putting it under a partial vacuum. If you're camping at high altitude, you will find that water boils at a lower temperature than 100, and your coffee or soup may not be as hot as they are at home. So, water boils, and other liquids boil, whenever their temperature is high enough so that their equilibrium vapor pressure just exceeds the total pressure above them. Okay, here's the puzzler, which you should be able to answer based on what we've talked about, based on what I've talked about. Here we've got the same jar, now with a regular lid. I've boiled the water and sealed the lid just like before. And it's been cooling a little, but it's still pretty warm. I put a cover on the lid just to try to keep the lid close to the same temperature as the water for now. So we'll assume that everything is in equilibrium. Now I'm going to make the water boil by putting ice on the lid. Oops. See that the water's boiling now. And the ice is melting. So, the question is, Why does putting the ice on the lid make the water boil? Woohoo!